All right, let's take a look at problem 2. So we're told we have two flash separators in series that operate at 1 atmosphere total pressure. The feed F1 into the first drum is a binary mixture of methanol water that is 55 mole percent methanol with a flow rate of 10,000 kilogram moles per hour. The second flash drum operates at T2 and the liquid product composition X2 is 0.15 mole fracs methanol. The temperature of the first drum is 75 degrees C. What is the fraction vaporized in the first flash drum and the total fraction of the initial feed vaporized? What are Y1, Y2, X1, and T2? And then we're told at this pressure of 1 atm, our system can be described using these two expressions. Okay, so this is kind of like problem 1, where we were given data that was X1 or Y1, and then we had T2 or T-bubs. Only here we're given an analytic expression. Okay, and so the one thing I might just note is that X here is just a generic composition. So in this top expression, you might think of X as X1, and in the bottom line, or T do, you might think of this as, say, Y1, right? Vapor composition. All right, and so this is just generic mole fractions methanol, which is component 1. Okay, all right, so let's kind of walk through this problem and set it up. I'll leave all the quantitative calculations for you, but it's good just to essentially draw our picture and try and figure out exactly what we have and how we would tackle this. Okay, and essentially how I'm going to set it up or think about walking through it is we're going to have two flash drums in series, and my goal is to characterize every single stream. Okay, so how are we going to go about doing that? So if I start with drum 1, since I have two drums in series, okay, into drum 1, I'm going to have some feed of composition Z1. Okay, coming off the top will be some vapor, V1, and that'll be of composition Y1. And then out the bottom will be some liquid L1 of composition X1. Okay, so let's just focus on drum 1. So in drum 1, we're given the initial feed. Okay, the feed's 10,000 kilogram moles per hour, and we're given the initial composition 0.55 mole fracs. Okay, so Z1, okay, 0.55. Okay, F1 we're given. I'm just going to check it. I'm not going to write it down. Then in terms of the drum, the pressure is 1 atm, and the temperature then is, so we'll call this T1. This is the 75 degrees C. Okay, and what I'm going to do is, since we have two drums, let's give all these, say, superscript, I don't know, A, our first drum, drum A. Bam, and we'll call that T1A. All right, so just looking at the first drum, our inlet specified, we know Z1 and F, okay, and inside the drum, we know the temperature and pressure. Okay, so we assume we have an equilibrium contact. So if I have a binary system at two-phase equilibria, how many degrees of freedom do I have? 2. Okay, and so if I were just thinking about a TXY, since essentially that's the data that we're given, okay, so again I sketch my picture of a TXY, so I can check the reasonableness of everything. Okay, taking component 1 to be the most volatile component. Okay, T1 sat, T2 sat. Okay, so in a TXY, pressure is fixed. The idea being, if I were to specify temperature, okay, so if I were to specify temperature and the fact that my system's in two-phase coexistence, right, it's a flash drum, it better be at two-phase coexistence, right, I would read off the value of X1 and Y1, X1 being read off from my bubble line, Y1 being read off from my dew line. Okay, so that's that. Here's bubble. Okay, so the first fact is since we're given both the pressure and temperature, then we're given two expressions that we can use to since we're given two expressions describing the phase equilibrium of our system, then the first answer is, well, knowing pressure and temperature, then yes, we can solve for composition. Okay, and so how would you do that? Well, remember, I read off vapor compositions for my dew line, and I read off liquid compositions for my bubble line. So in this case, we know the temperature, okay, and so since T dew equals T bubs, right? So I would have an A essentially T dew is equal to 75 degrees C, okay, and T bubs would likewise equal 75 degrees C, okay. And so you could go up to each one of our expressions here, okay, set them equal to 75 degrees C, and solve for the liquid composition from T bubs and the vapor composition from T dew. All right, so you have these two expressions that you could directly use to solve for, x1 and y1 at that given temperature. So if you're using MATLAB, right, you could readily use roots with either one of these animals. And then in this case, you should only get one real root. If you were to get more than one real root, remember your mole fractions are going to be between 0 and 1. Okay, cool. But you would solve those two equations for x1 and y1 by setting them equal to 75. All right, and so we would get y1 and x1. Okay, so then looking at drum 1, the only unknowns from there are going to be L1 and V1. Right? How do I get L1 and V1? I can get them via mass balance. Right? So if a binary system, I can write two mass balances for my system, either two component mass balances or a component mass balance and total mass balance. And since we have no chemical reaction going on, a mass balance is the same as a mole balance. All right, so to finish up drum 1, or let me call it drum A, I would simply have the F. And actually, so then this doesn't need a subscript, right? Because it's so the notation is bad. So actually, F1 in this case. So let's call F1, because it's the flow rate into drum 1. It's a Z1 mole fraction of component 1 in drum 1. Okay, and so instead of an A, let me put a 1 up there. Okay, because these refer to compositions referred to component 1 in drum 1. Okay, all right. So terrible notation aside, right? I could write down so this would be drum 1. I could write down a total mass balance F1 would be equal to so this is equal to V1 plus L1, and then my component mass balance, I would have that Z1 times F1 is equal to Y1 V1 plus X1 L1. Okay, so I know Z, then we know Y and X. We just found them from our equilibrium expressions, and we know F. Right, so I have a system of two equations with two unknowns that I can use to solve for V1 and L1. Okay, so I can completely solve drum 1 without a problem. Okay, all right, so I can solve, and I would get V1 and L1. All right, I have everything. All right, so now thinking through that further, now we're told that we have a second drum that operates at temperature T2, and the liquid product composition X2 is 0.15 mole fracs methanol. All right, so what's kind of unknown and a little confusing by this problem is basically we have one of two options. Okay, one option is I could take my vapor product from this stream. Okay, and let me draw a TXY and try and explain myself of what we might try and do with drums in series. Okay, and then I'll give you a spoiler alert based on having solved this problem already. Okay. And when you take 414, when you think about continuous column distillation, that's effectively having a bunch of drums in series or parallel. Well, series with countercurrent flows. Okay, so this is T1 sat. All right, so the idea is if I start out with some mixture of composition Z1, okay, and actually let me get myself closer to the middle, okay, and I heat myself up to the two-phase region, okay, I get phase splitting along an isotherm, okay, and so actually I'm going to make sure I label this point here, okay, where I read off my X1s and Y1s. I read off X1s from my bubble line, Y1s from my dew line. This point where X1 equals Z1, that corresponds to my bubble point. That gives me the largest possible Y. But if I continue to heat up from there, all right, I continue to get an X1 in equilibrium with the Y1. Y1's always greater than X1. Y1s are decreasing as temperature is increasing. Okay, and then the challenge is as temperature increases and Y1 decreases, well then the flow rate actually increases as well. Okay, but the general idea is, okay, and I could keep sketching this, is with this value of Z1, the largest possible Y1 value I could get is here. Okay, now if I started with the Z1, say that was here, and I heated up to my bubble line, okay, and this is where I apologize, my picture's not the greatest. If I had a mixture of this, composition Z1 that's greater than this Z1 over here, so if this Z1 was greater, and I heated it up to its bubble point, its Y1 value, okay, its Y1 max would be greater than Y1 max for the initial mixture. All right, so if I had a feed whose Z1 was larger, and I heated both up to the bubble point for those respective mixtures, the one with the largest Z1 would have the greatest Y1 max, right? The largest larger obtainable Y1 max. Okay, so one strategy then, okay, so let me erase this Z1 I arbitrarily drew. Okay, one strategy of putting drums in series, okay, would be, I'm trying to make my vapor phase as pure with respect to my most volatile component as possible. So one strategy then might be to take my Y1, okay, that comes out of my first drum, cool it down, okay, so essentially, condense it, and then send it into the second drum in two-phase coexistence. So the idea being in that second drum, the feed now would be greater than the feed to my first drum, right? So I know in my first drum, Y1 is going to be greater than Z1. Okay, so now if I take that Y coming out of the top drum and sent that into a second drum in coexistence, so in that case I would have to decrease its temperature until I enter the two-phase region. Okay, so if I were to take, say, this Y1 and cool it down, right? The idea again is, right, it would have the larger Y1 max since Z1 going to the second drum is greater than Z1 into the first. So it'd be a way, in theory, to increase the value of Y1, right? In theory. Okay. On the flip side of things, okay, what I could do, okay, and what's going to be done here, okay, so I get phase splitting along an isotherm. So we said, one approach would be I take Y1 and I send that into a second drum to try and increase the value of Y1. Okay. The other strategy would be to take X1, okay, and to send that into a second drum, okay, and then in that second drum, okay, what'll happen is, if this new, say, X1 were to become my feed to the next drum, well, what could happen then is I could actually get a liquid mixture which has even less X1, right, which would become more pure with respect to my least volatile component. So if I were to take, say, X1, and that became my feed to my next drum, I could, in theory, further decrease the concentration of X1 in the liquid phase, making that liquid more pure in the least volatile component. Okay, and that's essentially the strategy that's being done here. Is that we're going to take the liquid that's coming out the bottom of our first drum and send that into a second drum. And so the goal then of that would be to further decrease the mole fraction of component 1 in the liquid phase to make it more pure in the least volatile component. All right, so if I were to take, say, this liquid exiting the first drum, so X1's less than Z1 in the first drum, send that into a second drum, then we'd be able to move even further to the left on my bubble line. Okay, and so that's essentially what's going to happen here. And so, how this would look is, I would heat this up until I enter the two-phase region, at which point I would send it into drum 2. So the feed then to drum 2, I'll have, we'll call this F2, and F2 would be equal to L1, and it'll be of composition Z1 in drum 2, which would be equal to X1 in drum 1. Okay, so we're going to take the liquid stream exiting drum 1, send that into drum 2, where the temperature of drum 2 is going to be unknown. Okay, we need to solve for it. Oh, how the heck did I just do that? Okay, I do. Waiting for that to open so I can close it. Bam. Okay, so temperature there is unknown. The pressure again is going to be equal to 1 atm. Okay, coming out the bottom, I'll have some liquid. We'll call it L2. Be composition X12. Okay, and then coming out the top, we'll have a vapor. Call it V2 of composition Y12. Okay, and if I look at what we have, so we're given the liquid product leaving the second drum is 0.15. So I know X12 is equal to 0.15. Okay. All right, so now what we do next is we can solve drum 2, right? What's nice is we can solve drum 1 independent of drum 2 in this problem. And so thinking again, if I have a binary system at two-phase coexistence, I have 2 degrees of freedom. Okay, here I'm specifying pressure and I'm specifying liquid composition. Liquid composition counts as a degree of freedom. Okay, and so that means, okay, I can solve it for T in Y1. And so thinking about our TXY phase diagram again, okay, and now it's a matter of we're specifying X1. Okay, and so once I specify X1, I can solve for the temperature, right, at which I have that X1. Okay, and then once I know the temperature, I'll be able to solve for Y1. Right? But in theory, knowing X1 and the fact that I'm at two-phase coexistence is enough to pin down T and Y1 here. Okay, and so how you would have to do that is liquid compositions come from T bubs. Okay, my bubble point line or my bubble line. So basically now I would have to plug in X is 0.15, right? X1 is 0.15, so I'd plug in X is 0.15, and I would use that to solve for T from my bubble line expression. Okay, so I guess I didn't really have any notes. So the strategy here would be I could plug in X1 is 0.15 in this first expression, use that to solve for T. Okay, so then I have T, bam. Once I have T, then I go to my T-do equation. Okay, and I can replace the temperature with the temperature I just solved for. And then, I can set this expression equal to that temperature and solve for the composition, which in this case would give me Y. Bam. And then once I have Y, okay, I don't know V2 and L2, but, okay, for drum 2, we'd have the same mole balance, right? I can write down a total mole balance and a component mole balance and solve for L2 and V2. Okay, great. And then the last little caveat I think they ask for is what is the fraction vaporized in the first flash drum and the total fraction of the inlet feed vaporized. So I suppose this is a matter of how you want to call it. But if I wanted fraction vaporize in drum 1, Well, looking at the first drum, what fraction of the initial feed is vaporized? It's just what's coming out vapor relative to what went in liquid, right? Total fraction vaporized in drum 1 then would just be V1 over F1. Okay. And then they ask for total fraction of initial feed vaporized. Okay. Well, one way you could think about it is, well, the fraction liquid, so instead of maybe total fraction liquid, total fraction remaining liquid, would be what's coming out liquid in drum 2 relative to the total amount that was liquid going in. And so if I want the total fraction vaporized, then it would be 1 minus that amount. Right, so the total fraction vaporized would just be 1 minus that. Okay, yeah, cool. Or if you want to know what's vaporized, it should be that the total amount coming out vapor is V1 plus V2, right? So you could do V1 plus V2 over F, okay? Or if I do L2 over F, that's the total fraction remaining liquid, and I could do 1 minus that, okay? So hopefully that helps you out with this problem. We tackled it. We set up drum 1, saw that we could solve it independent of drum 2, then solved drum 2 using a TXY phase diagram again to help feel our way through the problem and check that we could answer each part. Hopefully that helps.